multi-stage delay. So now we have, if we have stages, multiple stages like this, something like that, some branching there, the final load through this path, we all calculate the effort delay, path effort delay, F1, F2, F3, F4, and F5. And then we also have a parasitic delay for each stages, P3, P4, P5. Now the overall path delay will be sum of those effort delay and path parasitic delay. So all the stages delay will have D1 equal F1 plus P1, and D2 equal to F2 plus P2, etc. like this. So D5 equal to F5 plus P5. So sum of all the path delay will be sigma of Di, that it would be effort delay plus path effort delay plus path parasitic delay. Now the designing the fastest circuit, as I mentioned before, the smallest delay will happen when each stage will have the same effort delay. So if you find the path effort and then take the nth 1 over nth root, that will give us the desired effort delay per each stage. So final minimum delay will be n times of the minimum effort delay plus parasitic delay will be that. So this is the key result out of our discussion. So the fastest delay will comes from by having the minimum possible effort delay, having the minimum. So the mean effort, the mean of so the minimum delay per stage, right? We don't consider without no parasitic delay. It will be the nth root of 1 over nth square root of parasitic f here. Path effort delay, right? Now the question is how we size the gate. So once we find the minimum, the optimum effort delay, for example, we have an inverter like this. The minimum effort delay for this stage is, let's say, F. So effort delay is defined by G times H. We know that C in and C out. If there is C in and C out, the effort delay and electrical H will be fan out. That will be C out over C in. We know that for inverter, logical effort is 1. So C in can be found by those results. So G in times C out over F hat, right? So F hat is our optimum effort delay. So we can easily find the input capacitance, and then by knowing this input capacitance, we can size that inverter, right? We will check, let's see how we will calculate. So in the next example, for example, we are dealing with this kind of a logic. So input capacitance is 8, and our load capacitance, final load capacitance is 45. Then how we size the x and y. So we will write down all the logical effort and electrical effort, logical effort for each stage, and electrical effort and minimum, optimum, and the stage effort, etc. So then based on that, we can calculate the x and y. Okay. So these are the things that we actually need to find out. So logical effort, electrical effort, branching effort. For this case, we know that how many branches there, right? We will see in the next slide in detail. So logical effort for NAND gate is 4/3. If you remember, that would be 4/3. I can show you some example. So 2-input NAND gate. So for equivalent driving strength with the inverter, you need inverter 1, so that should be 2 size and 2. So so the input capacitance of the one input is total 4 divided by equivalent inverter would be size of 1 and size of 2 PMOS, right? So that is the 3. Input capacitance is 3, so 4/3. Similarly, for 3 input NAND gate, we can find the logical effort 5/3, and another NOR gate, 2-input NOR gate, has the logical effort 5/3. So all the logical effort multiplication of all the logical effort will give us a pathological effort. So pathological effort we get this. So for electrical effort, we know the input versus output ratio 45/8. The branching effort, we have 3 branches here, so 3x total, 3x over x, right? 3x over x, that is the first stage, the branching effort. And here the second, the last stage, we have the 2 branching with the same size of the 2y over y in my path, that give us a branching effort 2. So path branching effort will be multiplication of all these. Now the path effort will be all the multiplication of GBH, that is 125. Now the best stage effort, optimum stage effort, will be nth root of the f, that give us a 5. Now we calculate the parasitic effort, parasitic delay for each stage, for each logic, that gave us 232, the total 7. So finally the total delay would be the total minimum delay, the best delay will be equal 3 times 3 stage 3 times and 5 from here, right? The optimum best stage effort, so 3 times 5 and plus parasitic path delay, so that give us 22. So this number is equivalent to 22, that is a fan out of full delay in 4.4 times of the fan out of full delay. So what we get is total delay is found like this, and now it's time to calculate the input, the x and y value out of this best stage effort. So we found from the previous example, we found that f hat is equal to 5, right? Best stage effort is 5. So we can work through to find out x and y, right? Based on that, we can find that. Let me go to in the next slide. So we found that f hat is 5, that is g times h, right? So g times c out over c in, so c in can be found g times c out over each stage in f hat. So for this 2-input NAND gate, we know that PMOS, the size of a 2, 2, 2, 2. For 3-input NAND gate, we know that the full equivalent inverter, that should be 3, 3, 3, right? And 2. PMOS 2, 2, 2, right? So we started from C in is equal to 8. So we know that the PN ratio is 1 to 1. So it should be 4 and 4 for 2-input NAND gate. So to calculate the X, so we have to back propagate from the last one. So we have to calculate the Y, so input capacitance, that Y determine the input capacitance. So we have a 2-input NOR gate. We have a 2-input NOR gate. For example, let's say 2-input NOR gate with the equivalent strength of the inverter should be like this. The size of 4 and 4, right? They give us equivalent inverter size of 2, 1, right? So we have a 1 to 4 NMOS and PMOS, the ratio. So let's find the Y input capacitance. So Y can be found by later 45. C out is 45, and C in is, let's say, Y. So we know the F head is G. G is 5/3 times C out over C in. So this from this equation, that is 5. That's what we have found. So we can calculate the Y. So Y becomes 15. So 15. To make this one 15, we know that input PMOS and NMOS ratio is 1 to 4. So 1 to 4. So 1 to 4. So if we scale by 3 times, then total capacitance would be 15, right? Once we know the Y, 15 load capacitance, now we can calculate the X in the same way. So this is the logical effort of the 3-input NAND gate. So this is G. 5/3 is G, and this is the C out of the NAND gate. So NAND gate have the 2 branching. So total input capacitance, total load capacitance of the 3-input NAND is 15, another 15. So total 30 is the load capacitance, and the G is the logical effort, and 5 is the optimum stage effort we found. So from this we can calculate the X, that is 10. So once we know the 10, so we can size the 3-input NAND gate, because the 3-input NAND gate will have NMOS and PMOS ratio. It should be 2 to 3, right? For example, we have a 3-input, 1 to 3, 1 to 3, PMOS. To make this equivalent to unit inverter size, it should be 3. Size should be 3, 3, 3, and PMOS should be 2, 2, 2, right? So we have a 3, 2, NMOS to PMOS ratio is 3, 2 ratio. So knowing this, total must be 10. So it should be 2x larger, right? So 6 and 4, that give us a total 10. So now we finally size the PMOS and NMOS. For in this kind of a procedure, we can determine how we optimally size those intermediate node gate, right? Now the question is, what is the best number of stage to minimize the path delay? So for example, for the given input, C in is 1 and upload is 64. We can have a choice of 1-stage driving and 2-stage driving and 3-stage driving and 4 stages of inverter driving. So for each cases, we can find out the minimum path delay. So in the previous example in the slides, we assume that we calculated optimum path delay. Now our question is, what would be the best number of stages to minimize? So we will find out for each 4 cases. So we know that the optimum delay can be found by the path effort, nth root of a path effort, right? So here in this example, path effort, no matter what the stage is f defined by the GBH, right? So here G is 1 and B is 1 and H would be the 64, all the cases. So we have the same equation. Now if we have n stages, then n times the stage delay effort plus n parasitic delay. For inverter, parasitic delay is equal to 1. So if we have n stages, then you will have n parasitic delay like this. So this is the example. This is the equation that represents the delay for each cases. Now let's plug in some number here. So for example, n equal to 1. Now the f would be, and the stage effort delay would be 64, and by adding parasitic delay, the total delay would be 65. For the second case, n equal to 2 stage, then f is from here. From the equation, we find the optimum. The delay would be, the stage delay would be 8. So we know that f hat is the nth root of 64, right? So we calculated this, that would be the 8. So if we have now, the total delay would be 2 times 8 plus a parasitic delay 2, right? So total 18. The third 3 stages case, now we have the f would be 4. So 3 times 4 plus 3 would be the delay, 15 path delay. From 4, if the n equal to 4, then we get the optimum effort delay is 2.8. So for 4 stages, finally we get the 15.3 as the path delay. Comparing those 4 cases, you get the third one would be best cases. This is the fastest, right? So about the fan out of 4 give us the best kind of the delay, fastest delay in this example. So in this example we just showed that the result, but let's just analyze more in detail in mathematics. So we'll drive the optimum stage n, and by driving mathematical equation in the next slide. Let's consider the certain n1 stages logic block, and at the end we have n-1 extra inverter stages. So total we have n stages of a logic gate. So the n-1 stages of extra inverter shown here, you can add this, or you don't. If you do not want, then you don't have to add those. So result doesn't matter whether you have a extra inverter there or not. So this is a generalized example. For example, if we have a delay, if we want to calculate the path delay, we will find the path effort. From that we get the optimum delay, the stage effort, right? And the root of f, right? So using that, plug in the delay, and the for the n-1 we have a parasitic delay here, an additional n-1, we will have an inverter parasitic delay. This is the total the path delay. We want to minimize this to we want to find the n that minimize this path delay. To find that n, So we use uh, derivative. We take the derivative of d with respect to n, like this. dd and dn equal to. You calculate that. So this kind of equation is shown here. So our goal is to find the f hat, right? First, what would be the stage effort? So if we define the f hat here, in this case we define that into rho, that is similar to f hat in the previous definition. We plug that rho into that equation. What we will get is this equation right here. So you want to find the rho satisfying that equation to find the minimum delay, right? So what would be, so from this equation we want to find the n, and that minimize is d, right? Let's see the next slide. So for given here, so rho is nth root of f. So no closed form solution. So in this case, let's say to make it simplify, assume that parasitic inverter delay, let's say, equal to 0. If we neglect the parasitic, then we find that rho becomes the 2.7, right? And for imp1, we now get the rho equal to 3.59. What this really means is so we find that optimum path delay using that actually defined by G times H, right? For the inverter, if we assume that all inverter chain G equal to 1. So that would be the H, right? 1 time H. So fan out, this H equal to C out over C in. That should be 2.7 natural constants E, or 3.59, considering P imp equal to with P imp equal to 1. So this gives us some guideline that if we want to have a minimum path delay, try to make the fan out close to 2.7 for no parasitic P, neglecting the parasitic delay, then 2.7. If we include that the parasitic delay, then optimum delay would be achieved, the minimum delay would be achieved by having fan out of 3.59. So as a rule of thumb, so fan out of 3 is kind of between those two cases, right? So as a rule of thumb, so fan out of 3 is kind of a starting point for designing your inverter chain for minimum path delay. Okay. So let's review that sensitivity. How sensitive is the delay to using exactly the best number of stages? So if the stage has if we choose the best number of stages there, then we will achieve the minimum delay. If we off by like this 1.4 or 0.7, 40% or 30% different stages, then we are getting just about less than 10%. How much? 15% variation of the 15% from the optimum delay. So we know that between 2.4. This is fan out of the fan out equivalent to fan out age. So 2.4 and between 6 gives us within 15% and error from the optimum delay, right? So people trying to use the we can choose that start from the 4. So 4 is kind of the number that if we consider the parasitic delay, right? Parasitic delay PMV equal to 1, then that gives us a starting point of rho equal to 4 electrical the fan out of 4 here. So if you have a little larger fan out, it can be little slower, but the one benefit is that you can use the smaller number of the stages, so you will get less power consumption. We will see later how the power consumption can be reduced. But for now, we choose to use in this example, let's say 4, then just it doesn't give us optimum minimum delay, just little off from the optimum, but that's pretty acceptable value. Okay.